Yeah. Hello, everyone. Can everybody hear me? Yeah. No, it's green, and it's very close to my mouth, so I don't know what. So it's not my phone for once.
It's working? Yeah. I can introduce myself.
All right. Doesn't work either. I don't know. Is that working now?
Maybe I can just use Arya's one quickly.
Yep.
Okay. So Arya, follow me around, please, because I'm using your yeah. Yeah. So I was going to say that Arya have known each other, and we have known each other since forever because we are students together in Switzerland at the University of Lausanne, and that's the perfect way of introducing the fact that we were little goofballs, and we are going to tell everything we have been doing. Yeah. But anyway, this is a very long-lasting friendship, and we bonded over our love for igneous petrology. And for as long as I have known Arya, she was all about Mars. So I am all about birds. Well, Arya is all about Mars. And when she was a student, Mars was her dream. And in terms of planetary science, Switzerland doesn't offer much. So when she got her master in 2010, she said, okay, where is the most specialist on Mars I can find? Hap McSween, Knoxville, Tennessee. And there she went, like at 22 years old, she went barely speaking English, and she went to follow her dream and do a PhD with Hap McSween. While doing it, she became one of the foremost petrologists on Mars. And when I say foremost, it's the truth. And she was so good that actually the University of Las Vegas gave her a faculty position even before she defended in 2014. And she has been at Las Vegas since then. And not only is she one of the best Martian petrologists around, one of her dreams came true recently when NASA selected her to work as a research scientist on the 2020 lunar rover. Martians, yeah, well, you know what I mean. So basically, Arya, what a journey you have made since we were students together. And I am amazingly proud to have you here today. It is our great pleasure to welcome you. And the floor is yours. And so is your microphone.
Thank you. Thank you all. Thank you, Melanie, for quite the introduction. Can you hear me? Hopefully it's good. Thank you so much for having me today. Hopefully, let me know if you cannot hear me or anything. Yeah, I'm really excited to be here today. Actually, for my PhD, I work with Rick in the Sims lab. Back at 2 a.m. In the morning to my hotel room, trying to measure lithium isotopes. I have fond memory of ASU. But today I'm here to talk to you about my favorite rocks, Martian igneous rocks. And before we start, I have to acknowledge the very large pictures of all of my former and current graduate and undergraduate students whose work I'm actually presenting today. You'll see a lot of bits of all their work. And I also want to acknowledge all my main collaborators, including your very own and wonderful Dr. Jim Davidson. We're going to start working when we'll work on MX rocks together. So I am myself an igneous petrologist. Okay, what does that mean? I work on magmatic rocks, but I work on Martian magmatic rocks. So what do I do on a daily basis? For those of you who are not igneous petrologists or even geologists, that means that the first thing I do, especially actually when I have meteorites. So I work on both meteorites and surface samples that have been measured by landers or rovers. But when I have meteorites, I look at them under the microscope. This is the first thing that us petrologists do, to look at what are, what is the rock, what are the minerals in them, what are their shape, what are the sizes, and all of that with looking at all of that, I can try to determine what is this rock, what is possibly the composition, and how it was in place. And then, of course, we look at elemental composition of the rocks, of the minerals. You can see here, this is a chromium map of a pyroxene, a very typical mineral that you find in Martian rocks. And you can see my graduate students here zapping with a laser a Martian meteorite. And this is to tell us the trace element analysis, the trace element composition of this rock. So really, I study Martian magmatic rocks for a living. So today, I want to tell you about this Martian magmatic rocks, all the different types. We're first going to talk about Martian meteorites, and those are the only samples that we have of Mars right now. So they are really, really precious. And I'll show you a little bit, even just having sample from another planet without full context, we can try to determine their emplacement. I'll show you how we can do that. We'll talk about also surface igneous rocks. And finally, I want to wrap up I'm going to talk about the importance of written samples, and especially written samples from Mars. So for those of you who don't know what meteorites are, so meteorites, they are pieces of other planets that have been ejected from impacting another parent body, in this case Mars. They will be ejected into space and then will land on Earth. Okay, they land on Earth all the time. Most of the meteor and the meteorites land into the ocean. But the easiest places to find them are actually deserts, where you don't have vegetation or where you don't have any other rock. So it can be cold desert and hot deserts. So how do I obtain my meteorites? There's kind of even three different ways. But I can have meteorite from Antarctica. So there's actually the NSMIT expedition that's funded both by NSF and NASA. Every year they go to Antarctica, at least when there's no issue with COVID, for 2 months. So they go camp in the middle of the ice and go around on the skidoo to look for meteorite. You can see here my friend Nina Lenza with a meteorite that she has found right there. Those meteorites are sent back to NASA Johnson Space Center, as well as the Smithsonian Institute, and then myself, you can make a request and say, hey, I want this meteorite, I want this thin section, so very thin slice of rock, I want this bulk rock to do a specific type of science. Usually, NASA want to give it to you because we want to do science with those rocks. It's not like money that is limited. If you ask for 15 kilos of one rock, we obviously, NASA obviously won't give it to you. Another way to obtain meteorites, especially the Martian ones, they are the Northwest Africa meteorites, or the NWA. So those, you can find them, they are found mostly by locals in Northwest Africa and the Saharan Desert. Those locals will actually go pick up those meteorites, sell them to dealers that will then sell them to collectors and scientists. So myself, I work with different meteorite dealers to obtain those meteorites. But also in your very own CMS, actually just borrow some rocks and also working with Dr. Davidson on some of those rocks. So question everyone has, how do we know that Martian meteorites are actually from Mars? So the first evidence that we had was back at the end of the 70s, early 80s, looking at those very weird meteorites. Actually, we're going to go back even further in time. The Viking landers, there were 2 landers that landed in the northern hemisphere of Mars in 1976. And those 2 measured the Martian atmospheric composition. Okay? And then we had those meteorites that are weird, knowing that most of the meteorites that we have come from the asteroid belt, they come from small parent body, they have a different mineralogy. But those ones were weird because the mineralogy, the composition showed that they came from a larger planetary body. And the obvious answer could have been Mars. We actually measured some little gas inclusion, little gas pocket inside minerals. Okay, some of those rocks, like cold sugar-type glass. We looked at the noble gas, carbon and nitrogen composition, and you can see that it fit completely the Martian atmospheric composition that were measured by the Viking landers. Okay, and this is where we had the first evidence that we have Martian meteorites from Mars. Now we don't really use that. I'm not going to look for gas inclusion. They're not easy to find. They're not easy to measure. We can use simply the triple oxygen isotope composition. So you're not a meteorite person. meteorite folks, we all use this to know what is the parent body of our meteorite, because each different parent body, different kind of asteroids, as well as the moon, Mars, have different triple oxygen composition. So we use meteorites because they really can tell us about many geological processes on those parent body. And in this case, really on Mars. They can tell us about the emplacement and formation of magmatic rocks. They can tell us about volcanic processes, diversity of sources. So when I talk about source also exists on Earth, those geochemical sources. So if you look at in the interior of the Earth, there's those geochemical pockets with different composition, different elemental and isotopic composition. And this is what we call a source. So, interior of planets can be very well mixed, or can not be well mixed. So on Earth, we have plate tectonics. It's quite complicated. So we have a lot of different sources. And actually, we've noticed that on Mars, there is a lot of them as well. We can look at volatile processes, alteration processes. I don't really look at those, but they're very important to understand what's happening at the surface of Mars. Impact processes. And finally, as we can measure those rocks in the lab, in very highly precise lab, we can also measure the timing of those Martian meteorites. So, and obviously during this talk, I'm gonna talk to you a lot about Martian rocks. That's all I'm gonna talk about as well. So I'm gonna use certain terms, and I wanna make sure that everyone know what those terms are. So first, Martian ages. It's quite easy, it's much easier than the Earth. It's only 3 ages. We're going to start from actually younger ages, the Amazonian, which is between 3 billion years old and now. Not that much has happened during that time. We have the Hesperian, that's between 3.6 or 3 billion years old. I say this can be 3.6 or 3.7, depending what you read. And then before that, it's the Noachian, or Noachian and pre-Noachian. And during this time, during the Noachian and pre-Noachian, so really between 4.5 and 3.7 million years old, this is when a lot has happened on Mars. A lot of volcanism, a lot of impact processes. Probably that's when there was the most water. And if there was ever life, that's probably when that was, during the Noachian. Okay, so remember, Noachian, Hesperian, Amazonian. I'm mostly going to talk about the Noachian. You don't know really rocks really well. If those of you are not geologists, I want to just kind of do a review for you, because I'm going to use those terms a lot. Mafic and felsic. So when we talk about igneous rocks, we use those terms, mafic and felsic. Mafic rocks, they're going to be rich in iron and magnesium, like a basalt, like what you'll see in Hawaii, craters of the moon. Whereas felsic rocks, they're going to be lower in those elements and higher in silica. They have actually undergone much more complicated magmatic processes, a granite, a rhyolite, I have a bunch of them here. Those are felsic rocks. Mafic and felsic, they're based on the composition. We also use terms like plutonic and volcanic, or intrusive and extrusive. Those just represent where those rocks have crystallized. So plutonic rocks have crystallized under the surface, and volcanic rocks have crystallized above the surface, okay? Intrusive rocks inside, extrusive rocks outside. That's simple. And now I'll talk a lot about those 3 minerals. If you want to learn minerals, I would say those are the 3 main ones you can learn. You can also learn quartz. There's olivine that we'll find in those Martian meteorites. You also find them in basalts everywhere. There are green in hand samples. If you go to the beach in Hawaii, there's this green sand. It's all olivine. It's enriched in magnesium and iron. You also have pyroxene, quite not the most beautiful minerals, but the most interesting in my opinion. They're enriched in iron and magnesium, and they're black in hand samples. And then plagioclase. You look at the moon, everything that's white, that's all plagioclase. Those are enriched in aluminium, calcium, sometimes sodium. Okay, and it's the most common mineral in the Earth's crust. So I'll use pyroxene, olivine, pyroxene, and plagioclase, typical mineral. Okay, let's go back to Martian meteorite. So right now, we have recovered 221 Martian meteorites. It's actually not that much compared to most of the complete meteorite collection that we have, which is about 73,000 right now. And most of those rocks come from the asteroid belt. Obviously important study, but I wish we had a little bit more. But if you look at this graph, so you have in x-axis the year those rocks were found. It's not continuous. The first one that was found was Chassigny that was found in Chassigny, France in 1815. At this time, we didn't know that it was Martian meteorites, but I guess somehow they figured out it was a meteorite. And in y-axis, you have the number of meteorites. So one thing that you can notice on this graph is that in 2014, there's been a peak in finding those Martian meteorites. I was talking to one of the meteorite dealer who told me that a lot of those rocks are Northwest African rocks. And apparently people who look for those meteorites have been more and more educated about how, what Martian meteorites look like. Those Martian meteorites are more expensive, so they want to try to find more. And we have found a lot more, obviously, and then there was COVID, and then it went down. And as of all of those, there's only 5 that observed faults. We observed them landing on Earth. And the last one was this in 2011 or 12. So what are those Martian meteorites? There's 3 main groups. Some of you might have heard the SNCs. I don't like using SNC because they're a little bit more complicated than that now, but there's 3 main groups of Martian meteorites. The sugatites, the nuclite, and the chassignites. A lot of terms I know today. Sugatites, I mean, all those names are defined by the first meteorite of this group that was found. So sugatites, the main one was found in Shagati in India. Nuclite, the first one was found in Egypt, in Nukla, and then chassignite was Chassigny in France. Okay, those rocks are relatively young. Most of them are younger than 1.3 billion years old. It's actually quite young for, planetary rocks. There's only 2 that are 2.4 billion years old. And then we have single meteorites. Allen Hills 84001, this one's a really cool one, and it's quite old. It's 4.1 billion years old. Remember, it's pre-Noachian, Noachian, depending what you use. And then the beautiful NWA 7034, and it's paired meteorites. By the way, if you don't know what a paired meteorite is, it's when a meteorite enter the atmosphere, sometimes can break down different pieces. Those are all paired meteorites. So you can have, in this case, it's actually 18 paired meteorites. They all come from the same paired meteorite that broke down into the Earth's atmosphere. This one it's a polemic regolith breccia. So breccia is made of a bunch of angular clasts that all come from different previous rocks that were all assembled together. And some of those clasts are 4.5 billion years old. This is older than the oldest minerals that we have on Earth, which is quite cool. So all those rocks, they're magmatic rocks, okay? They form from crystallization of lava or magma, okay? They are basalts or gabbros, except this one, which is that weird sedimentary rock, but still all have igneous composition. That's NWA 7030. So the problem with Martian meteorites is that we don't know where they come from. We know they come from Mars, but that's quite a large planet. So here, this is pretty much a topographic map. You have in blue the lowest elevation, in white and in red the highest elevation. And I put in purple all the different spots where the different landers and rovers have landed. Again, we don't know where those Martian meteorites come from, but it potentially could come, a lot of them could come from the Tharsis province. You can see here, that's much higher. It's actually quite a large bulge, because this is actually much younger than the rest of the planet. So let's look at what those different Martian meteorites are. First, the sugartite. The sugatites, they're the most common type of Martian meteorites. They consist of 88% of the whole collection. Their age is between 150 million years old to 2.4 million years old, but most of them are younger than 700 million years old. So remember that pretty much more than 85% of the Martian meteorites are younger than 700 million years old. That's very, very young. And they're really basalt. They have all the minerals that I told you before, olivine, pyroxene, hydroclase. This is a beautiful example of, this is a gabbaric rock, NWA 6963. So this is an X-ray map. So in green, you have iron. I'm sorry, in green, you have magnesium. In red, you have iron. And in blue, you have calcium. And so you can see all of those are actually pyroxene that have accumulated. This is an intrusive rock. Then we have my personal favorites, nuclites and chassignites. So the nuclites, see it right here. This is a clinopyroxene-rich cumulate. And then the chassignites are dunite, so they're mainly made of olivine, that green mineral, okay? Those two types of rock, they actually have geochemical and textural similarities. But what's cool with them, they all have the same crystallization age and they all have the same ejection age. So they all have been ejected at the exact same time from Mars. That means that they likely all come from the same volcanic province. Okay, and that's cool to study all of them together. In total, 35 individual rocks, because if you study all of them together, it's kind of like studying a terrestrial rock. When you go in the field, you're not going to go take one rock and go home. That would be quite lazy. You want to, collect a suite of rocks. You can kind of do that with those rocks, and they're really cool again because they're petrogenetically linked. And I'll tell you more about those. There is also, remember those single meteorite, Allen Hills 84001. This was found in 1984 in Antarctica. It's very old. It's 4.1 billion years old. Its magmatic history is not that crazy. It's also pyroxenite, so it's mostly made of pyroxene. But the thing is that we found, carbonate globules with little magnetite in them were found in those rocks. And this was back in 1996, argued to prove that we had life on Mars, because those magnetite could have possibly have been formed by magnetobacteria, which are little bacteria that produce magnetite. Later on, it was proven that it was completely abiotic, but this actually helped really push forward the Martian exploration. Because after that, we had the Pathfinder lander, we had then all the Spirit, Opportunity, Curiosity, all of those different rovers. And then one of my favorite as well, we have the Polemic Regular Spreadsheet, NWA 7034, and it's 17 paired. So this one is really cool because it has all those classes. I was telling you about those classes. You can even see them in hand sample. This is, this is not simple. It has this beautiful fusion crust. The fusion crust is when a meteorite enters the atmosphere, it's really hot, so the outside will melt. That's how you can recognize a meteorite. And it has the oldest Igneous class from Mars. So by studying those classes, we can understand the very early evolution of Mars. It's really cool because we can not necessarily do that with terrestrial rocks. What we have from the Hadean is a bunch of little minerals, the oldest time on Earth. So by studying this rock, we can better understand Mars, but also understand a little bit possibly the Earth. So I want to show you a little bit what we can do with Martian meteorites. We don't have field context for those rocks, which is what we usually want when we do geology. But we can look at different tools, use different tools to understand the emplacement. And I'll show you an example of especially what a lot of my grad students have been doing on the nuclides and chessignite. I'll just put some image again to show you. So what we did first is looking at the mineralogy of all of those, looking at what mineral formed first. And that's something we can do by looking at the chemistry of those minerals, the ball composition, and also the textures. Okay, so how large the grains are. And through that, we can actually, it was previously shown, that they all come from one single lava flow. And we actually showed from that they come from several lava flows. I drew that on one volcano. We can be a bunch of different volcanoes from the same volcanic province. It can also be sill, which are intrusive, lenticular bodies inside the Martian crust. And you can see that they're actually much more complicated than we previously thought. But the thing is that we look at, we did that by looking at thin sections. So it's a thin slice of one tiny rock. That's all we have. That's all we have, but actually we still have a chip. Usually I make my slice from a little chip of it. So why not look at the entire chip and look at the texture that we have in it? So we can do actually 3D X-ray computed tomography analysis. So it's pretty much doing a CAT scan of your rock, and this is my favorite thing to look at. So this is work that's going on right now with my PhD students here. Ramsey is doing. So what you see here, this is a nuclide, the NWA 13369. In gray here, you have the pyroxene in lighter gray. You have olivine in darker gray or black. You have the glass of plagioclase, and the white, you have oxide. Okay, and when you see that moving, imagine you have pretty much hundreds, thousands of slices that you can look at. And from that, you can see, for example, how the pyroxene, what is the direction, the length of the pyroxene, much more than just looking at one single 2D slice. So actually, by looking at those, we looked at a bunch of different nuclides. We can see that some of them had foliation, lineation, or completely random. If you don't know those terms, that's okay. Just to show you that from that, we actually realized that the emplacement of nuclide and chessignite is quite complicated. It could have emplaced in a magmatic chamber, in a sill. So magmatic chamber, imagine this big pocket, this really large pocket inside the Martian crust, a sill or a dike, or it could have been a lava flow, it could have been a lava lake, or all together, a combination of some of them. They're actually quite complex. When we compare them to the sugartites, remember the sugartites are the most common type of Martian meteorites? All of them show that they form through gravity settling, which is what you will find, for example, simply in a magmatic chamber. Okay, so those we were able, by looking at them in 3D, to determine that they're actually quite complex. Obviously, it would be great to go in the field and say more than they are quite complex, but that's what we have. We can also look at melt inclusion. So those little folks right here, they're quite small. They're little trap pockets of magma that sometimes have crystallized, sometimes not. We can analyze them, analyze their composition, and try to infer what was the pantol melt composition of those rocks. Okay, before there's any other magmatic processes happening. I know there's a lot on those graphs, but this represents the nuclides and chessignites, and this represents the sugartite. They have the same axis, so left sugartite, nuclides and chessignite, I'm sorry, for the one online, and right you have the sugartites. So next axis, both you have zirconium over yttrium, and niobium over yttrium in y-axis. You don't know those elements, it does not matter, those are trace elements that we often look at to determine source of rocks. What you can see from afar on this gigantic screen, you can see that the sugartites, they all kind of, the melt inclusion, all kind of have the same trace element composition. Versus the nuclides, it's completely all over the place. So we know here with the nuclides and chessignite that we had likely diffusion happening between the melt inclusion and the host mineral. And that the take-away message, the take-home message from this slide is that those nuclides and chessignite have undergone really likely longer storage time, much more than the sugartites. Actually, when you look at the nuclide age, I told you it's about 1.3 billion years old, but actually their formation lasts about 100 million years old. So imagine a volcanic province producing magma for 100 million years old. It's actually really long compared to Earth. And that's one thing that we can do with those melt inclusions. We can also look at the distribution of those elements within those minerals directly. Those are elemental maps, and we use minor elements that do not diffuse with time. So for example, we can look at phosphorus in olivine, or those are quite new elements that we've been using, so those maps take a long time to be made, but this is a chromium map in pyroxene. So you can see, especially at the top, you have, enrichment, chromium, then depletion, then enrichment again. And then that means that this actually was quite a complicated history when the pyroxene was growing. So at first it was growing, it has a lot of chromium to take, a lot of chromium available. Pyroxene loved chromium, so it took it all. And then somehow it was a depletion. Maybe it was ascending and it was not able to get the chromium that it wanted. And then there was a recharge of magma. Imagine some magma coming back into the magmatic chamber, again, a large pocket of magma under the Martian crust. And then, enriching again the chromium availability in the magma. Just to show you that just by looking at those minor elements in those maps, you can kind of infer what was the complicated stories of this mineral as they grew from nothing to what you now found in those Martian meteorites. So really, with the Martian meteorites, we're cool. There's quite diverse lithology that we have found, actually, as you can see, especially with those crazy polemic breccia. From that, we would infer that the interior was actually more heterogeneous than previously thought, especially with most of the meteorite that we found since 2014. And that we actually have emplacement that's similar to terrestrial rocks, because everything I showed you in the melt inclusion, those chromium maps, the X-ray tomography, we've compared that to Earth to have a calibration. The problem is that there's some limits with those Martian meteorites. First, it's not that many. They're very young. You know, I told you that most of them are younger than 700 million years old. But most of the, I mean, actually more than 50% of the Martian surface is older than 3.7 billion years old. There's a lot of it missing. Okay, I mean, we don't have anything from 4.1 to 2.4 billion years old. We're missing half of the geological history of Mars there. And there's also, the composition is slightly different from what we measure from the surface. You know, the low end alkali, iron, calcium, it's a little bit all over the place. And also, we can infer some things from the mineralogy and the texture of those Martian meteorites. We have no field context. I'm still not sure what those nuclide and chestinite I've been looking at since 2010. I still don't know if they're intrusive and extrusive, which is something when you go in the field, you can kind of directly see and boom, it's done, you know. And we're also missing a lot of the lithological diversity. At the surface of Mars, we actually have found rocks. You know, I told you about mafic. Most of the Martian meteorites are mafic. Well, we found some felsic rock, some alkali-rich rock at the Martian surface, which we do not have in our sample collection yet. So what we can look at igneous rocks from the surface. What about them? Well, first, where are they? So hopefully you can see this is on the far right. You have, we can look at the Spirit rover that landed in Jezreel Crater in 2004, the Curiosity rover that landed in Jezreel Crater in 2012, and then the Perseverance rover Mars 2020 that landed in Jezreel Crater, another crater, in 2021. So all of those actually have found igneous rocks, different location, more or less. First, you have the Spirit rover that found, you know, we landed in this crater thinking it would be a lake, thinking we'll find a bunch of lacustrine sediments, and we're able to, and so, you know, the better understand the water history of Mars, and then what we found is a bunch of lava flows. It's great for igneous petrologists. This is what we found. The Curiosity rover have found a lot of float rocks. So float rocks, that means, you know, when you go in the field on Earth, you want to go on an outcrop where you actually have the field context. A float is just a rock that's there, and you don't really know where it comes from. This is mostly what we found in Jezreel Crater for the igneous rocks. But a lot of them were really interesting. They were very potassic rich for some reason. They had very different composition than what we found in Jezreel Crater and also in Martian meteorite. And then Perseverance rover, I'll tell you more about those rocks, but the first year it was all igneous rocks. We found potentially lava flow, pyroclastic flow, potentially cumulate, with all the minerals that you've learned before, olivine, European, and hydroplace, which was great. And you can see here being all proud, having drilled Montagnier and Montagnac. So those rovers are great because we can analyze in situ those rocks. We can have the field context. We can take pictures and all. We can do almost live, you know, geological work there. But really, the problem is that there's also a limitation here. We cannot do high precision analysis of those rocks. You know, once I show you the trace element analysis, those are extremely important when you do geology. When you try to understand the formation of rocks, you need to measure trace element. Trace element means that they are in very small concentration in those rocks, and thus they're difficult to measure. And for that, you need Earth-based laboratory to measure those trace elements, those isotopic composition, to understand the age of those rocks. Okay, and that's the main problem. So what do we need? We also need the state-of-art geochemical, petrological, and geochronological analysis. So for that, we need return samples. We need to go there, which we are doing right now with the Perseverance rover. We're drilling some rocks, and hopefully we will bring them back. And we can then analyze them in the lab. So we will have the field context. We can have a larger range of ages, especially in Jezreel Crater, where we have potentially from, you know, mid-Amazonian to the Noachian. We'll see what we find, you know. We cannot measure the age right now. We're not really sure how old they are. We have ideas. But we have a larger lithological diversity from that. And we're finally going to have sedimentary rocks. And sedimentary rocks can tell you about surface processes of Mars, the water history on Mars, which is super important, and possibly show maybe we'll have biosignature from Mars. Who knows? So we can do precise Earth-based laboratory analysis. Okay, isotopic analysis, determine age, and everything I told you about before. And also better definition of Martian crater ages. So you know how we date planetary surfaces is using crazy cradle counting. Really much simplistically, it's like the more craters you have, the older a surface age is. Okay, and everything is calibrated from the moon. We can see the moon, we can see how much crater it has, and we have brought back samples directly from it with the Apollo samples. But we need to do that for Mars as well, because we're using the lunar calibration, which is not ideal. So we talk about return samples, we have to talk about Jezreel, as you can see right here, that landed about Jezreel, about the Perseverance rover that landed in Jezreel Crater in February 18th, 2021. So I'll tell you mostly about the first year in Jezreel Crater, because this is where we looked at igneous rocks. So we found actually two potentially igneous formations to make sure, hopefully we'll have the return samples to be sure that they actually are igneous, but there were the mass formation and the Zeta formation. So where actually the quadrant is Canyon de Chelly, which is in your state. And this is, all of those are Navajo words. So Maz means moss in Navajo, and Zeta means amongst the sand dunes. So we landed here in Octavia E. Butler landing site. And you can see all those different soil. Those are Martian days, so about 24 hours and 38 minutes. We went down this way on Mars, and then we entered the Zeta formation. We went back and then up to the delta. And so during that time, we have sampled all of those different rocks, those different green and purple points. Okay, so let me tell you a little bit more about those rocks. Especially, I focus on the SuperCam instrument, which is really cool, which looked at geochemical data. It actually just sent this laser. You can see right here, this is a LIBS, so laser-induced breakdown spectroscopy. So pretty much gonna, from like, it works from 2 to 7 meters in distance, 1.5 to 6.5 meters. And will transform your rock into a plasma. The plasma will emit a light, which will have a spectra, and you can translate the spectra into a composition. So able to have 1,057 LIBS analysis, as well as a bunch of remote micro imager images that you can see right here in the lower right corner. So from that, we were able to look at textures. Obviously, we don't have thin section. This is quite cool to see. Oh, this is quite pixelized, I'm sorry. But you can see, what I want you to look at is that there's just a bunch of different textures in the mass formation. A lot of different ones that actually different grain scale, coarse grain, finer scale. And actually, some of them have little, look like it has gas bubbles, which call that vesicles, which potentially showed that there was degassing. And so this, with a lot of other field observation, we think that those are possibly thick lava flows with coarser grain texture in the middle of those lava flows, you know, that they are longer, so we can form larger grain that way, potentially with some pyroclast as well. We have found some lineation in some areas. So this is what we think there is, a bunch of different lava flows on that. We have other example here. This looks like a Paueoe lava. You can see in this beautiful image, and this is actually an image of Zeta that looks like it potentially has this cumulative texture that you can see also on Earth. If we look at the bulk rock composition, I'm not going to spend too much time on it, I'm talking too much, but here you have in this one, so you have silica over alkali elements, magnesium over aluminium, calcium, and iron. All the Jezreel rocks are in orange, versus all the other rainbow color points are all meteorites. Okay, and what I want you to see is just that they have slightly different composition than the meteorites. They have less magnesium, they have more alkali. Okay, they have less calcium than all those Martian meteorites. They're slightly different. We can also measure those single minerals with those LIBS. We can, from stoichiometry, we can infer which one only consists of one mineral. And we can, for the pyroxene, we can plot them on this pyroxene quadrilateral with, in the lower left, you have magnesium, the lower right iron, and the upper triangle calcium. And you can see the mass points are all in red right here, actually really rich in iron. And even if there's an instrumental error that would place them right there, which is still extremely rich in iron, which is really weird, and I cannot really fully understand, except symplectite for the petrologists in the crowd, what those are. So I really want to see those samples back to understand why are those compositions so weird. They're similar to some of the pyroxene that we have measured in the Martian meteorite, but they're still very iron rich. And in the mass formation, only found one plagioclase, just one, that plot right here, and just have a similar composition as the other Martian plagioclase. So what we have in the mass and the zeta formation, we think that both of them are igneous, but who knows? We're open to. I'm open to other suggestions. With the zeta formation below, with the mass formation on top, that possibly have different lava flows as well as pyroclast, which is quite cool. We found igneous rocks. The thing is, those rocks have different mineralogy, slightly different bulk composition than the Martian meteorites. They also different ages. One of the last paper mentioned that the crater floor where we found those rocks could be potentially between 2.6 and 3 billion years old. So it's older and much older than most of the Martian meteorites. So those rocks are really important for sampling. They can help us about understanding the chronology of those rocks and the igneous activity at this time on Mars. And right here, I'm just talking about the igneous rocks. So we actually have sampled eight igneous rocks from Mars. So a little drill that you can see right here. This is Montagnier and Montagnac that have been sampled. You can see this drill. Just 8 igneous rocks, but there has been much more, obviously. We have sampled one atmospheric sample. We have 8 igneous rocks, are both intrusive and extrusive, very likely to be proven, obviously. 9 sedimentary rocks, okay, that can tell us about the surface processes, water-rock interaction, possibly biosignatures. We have sensors, siltstone, mudstone. Those are more complicated, and 2 regoliths, so representing on the top surface of the Martian surface rocks. So we actually have in total 38 samples that will be collected, are possibly to be collected, and 5 witness tubes. So only 52% of the tube have been filled out. So we are going up and filling those tubes. So we have actually deposited all those samples in, not all of them, I'm sorry, 10 of the tubes in what we call the three forks sample depot. So in case the rover gets stuck somewhere or whatever, we can actually land here, pick up the samples, and bring them back to Earth. So that are kind of our backup sample. The rest is still inside the rover. So what about the Mars sample return program? So right now we're collecting the sample, we're doing the geology, and potentially, it's not completely sure, but potentially we'll bring those samples back, okay? Back in 2028 or 2029, never remember the time, we're gonna have a lander that will take those samples from the rover. We're also gonna have potentially two little helicopters that look like Ingenuity, which is the helicopter that's now following a Perseverance that can also help collecting the samples depending on where the rover is. Those samples will then be put in the Mars ascent vehicle that will be sent into space. Those samples will be intercepted by the Earth Return Orbiter ERO that is actually made by ESA, the European Space Agency, and then sent back to Earth, back potentially in 2033. So everything has to work, and hopefully it will. So where are we right now? When we talked about the igneous rocks, we were right here. And we're going up the delta, and we're gonna, arrive in the crater rim relatively soon. We're gonna have very interesting, hopefully, rocks, potentially in Wacken crust. We'll see what we find. But right here, this is mostly has been all sedimentary rocks. And here, this was, by the way, a rapid traverse when we didn't do much. Today is Sol 892. So we've been here for quite a while already. So we're gonna have 38 samples from Mars coming back to Earth, potentially in 2033. We're gonna have diverse lithologies going from atmospheric, igneous, sedimentary, regolith, and who knows what else we're gonna find. We have obviously some beautiful igneous lithologies and igneous composition, and potentially rocks from the Noachian to the Amazonian to really understand the geological history of Mars. So really the complementary study of return samples and those meteorites will help constrain the geological evolution of Mars. I also want to conclude about the fact that those return samples from Mars is not just cool for me, just a Martian sample scientist on my, by myself. It's also important for the entire Martian community, but also most of the planetary science community. Because if we better understand Earth and Mars using those return samples, for example, the atmosphere, when we look at the Martian atmosphere, we can better understand the inner solar system atmosphere and thus better understand the outer solar system as well. So hopefully I can convince you that studying Martian samples are important, and returning those samples back from Mars are even more important. And thank you very much. I'll take any questions.
So if you do have a question in the room, there you go. We're going to use this microphone. I'll pass it around.
Hi, great talk, by the way. So the fractionation history of heat-producing elements in Mars is something that's still not really well constrained, like between the crust and mantle. And some geophysical and mantle evolution models suggest that up to 60% of the heat-producing elements, potassium, thorium, and uranium, are in the crust. Is there any way that you might be able to infer the fractionation history from the returned samples? And do you think that would be representative of the crustal depth? Or do you think that there may be variation with depth that we're not capturing with these samples?
Well, that's the problem. We don't know exactly where, especially where those minerals have been formed. We need, I think we need more experiments that are being made on geobarometry and geothermometry. But we could do that actually with meteorites. But obviously, if we have, from Noachian to Amazonian going through the Hesperian, we could see actually how potentially the heat-producing elements have also evolved throughout the geological history. I think that could be important.
Do you see a large variation in meteorite samples of the heat-producing elements, or is it all mostly chondritic?
I think they're mostly, well, the potassium is really high.
Yeah.
The potassium is weird. We can talk about it more.
Thanks.
I have a mic, so.
Was it?
It's a great talk, Arya. When you show mineral chemistry from the LIBS data, how are you getting that? I mean, are you sampling single minerals and then doing some sort of norm calculation? Or?
Yes. So
but you're sampling single minerals.
So the only way that we know is through stoichiometry. So somehow, by chance, it might not be a pyroxene or cannot find hydroclase. Only found one. I think they're too small.
What's the spot size of the?
It's between 170 and 350 microns. So it's quite small,
okay.
Which is a really large microprobe beam. The thing is, we cannot really see them. There was this rock in Jezreel Crater that's this beautiful hydroclase that you could see very well, but we haven't really found that in. Well, we found some olivine. You could see that. The pyroxene, it didn't show up in the remote micro images, unfortunately, but it was all through stoichiometry. So, there's a possibility there might not be pyroxene, that is just chance, but the stoichiometry fit perfectly a pyroxene composition.
This is a question which seems simple, but is impossible to Google. Are there meteorites from Earth?
There's terrestrial, on Mars, I don't.
On Earth.
On Earth, yes, there
So
are.
if you go looking.
Meteorites have been ejected and
Yes.
came back.
Okay. There are.
They are.
Okay. Cool.
What are the most recent Martian meteorites that have been discovered so far, as in samples that have been found across the solar?
So the Martian, we found Martian meteorite. I don't know who asked the question. I'm sorry, but sorry. It's the latest one. I don't know exactly, but that was that last year.
Oh, I meant on the geologic.
The youngest, 150 million years old. It's young, it's super young. And a lot of them are actually around that age, between 200 and 150 million years.
Hi, so do we know what kind of impact or impactors have caused the meteorites to be ejected from Mars?
No, we actually don't. It has to be a certain speed, which, again,
Okay, thank you.
it has to have a certain speed, but yeah, we don't know what was the impact of.
It's deep there, all the way at the bottom. No, Tom.
So this is a follow-up on the pyroxenes from the libs. It seems really weird to have these pyroxenes so rich in ferrocylite and so on, but your Martian meteorite had data there too. So how do you explain Martian meteorites with such iron-rich pyroxenes? I mean, it looked like there were gabbroic shergottites and olivine ferric shergottites that had similar pyroxenes, right?
Yes, but they were symplectite.
They were what?
Symplectite. So the late stage symplectite with also
Oh.
edendrite. There's also, phyllite and silica in those kind of those blobs. The late stage textures, which is really strange because how can we measure that? If we have symplectite, then we could, but how can we measure exactly? So that's why I'm not sure what's happening there. Why we need the samples back. I need the samples back.
So Mars meteorites, the oldest ones, Noachian or so, we know the atmosphere was very different back then.
Mhm.
Are there actually trapped gases of that atmosphere, or were they trapped on their way out? So what are there gas inclusions in the Noachian meteorites that have a different atmospheric composition?
A good question. In Allen Hills, I think the noble gas, carbon and nitrogen has not changed much. I do not know the other, I should probably, but I do not know the other isotopic composition. And for Black Beauty, it's a complicated one because it has, the class are old, but we think that the whole thing has been assembled between 1.7 and 1.5 billion years old. So things have been disrupted during that time as well. And we don't know if it was assembled through some sort of impact or pyroclastic activities. It's not really clear. That's a good question. I'm not sure.
Hi. So I was wondering, I think you said at one point that most Martian meteorites we found are younger than 700 million years old. Does that correlate to a specific geologic time period of Mars, or is it more of just like a recency bias, or do we have no idea?
We don't know. That's the problem with Martian meteorites, the complete bias of the Martian crust. One idea is that, let me show you. When you if you look at the topo map, I told you there's this volcanic province here, just bulging. It's bulging so much that it actually deformed the Martian surface. All of that, some of the youngest flow are 1 million years old. So all of this is quite young. So probably most of those Martian meteorites come from this volcanic province. One thing too, is this much higher in elevation. I mean, we have Olympus Mons right there, that's 26 kilometers in height. So they potentially are easier to eject when it's high elevation. So that's one possibility. We don't know. That's a good question. There's no clear correlation with any geological event. Most of the volcanism happened before 3.7 million years old. We don't have anything from there yet.
You mentioned that you really need to get the samples back to Earth because we can analyze them better on Earth. We can only get a small amount of samples back. But if we could put more scientific instruments on Mars, you could do work as well. how big is the lab that you would want? Is it a building? Is it a campus? Or is it a, like what's the range there?
If we could go to Mars and
Build your lab on Mars.
I mean, my own lab, there wouldn't be much, but I guess other disciplines are also important somehow. I did microprobe, laser, some people to do, they would be, I know Igneous rocks much more, but we would need a whole campus. There's going to be so many, and that's a cool thing. Like, it doesn't matter what, if you work with rocks, doesn't matter if you work on Mars or other planets, you can work on those rocks because we need input from everyone, especially the terrestrial geologists, to be honest, because we need a more broader input. And that in the prime, we all work on our planet, and I'm realizing sometimes like, oh, this has been done on Earth like 10 years. I had no idea. We can apply that to Mars. This is really cool. We also focus on planets, so we need everyone to work on it. We need a very large campus. Yes.
Hi, my name's Eli, and I have a question regarding the olivines that we find in these meteorites. I'm not too familiar with it. So are the olivines that we find produced from the impact, or is it already like included within so it's coming from Mars, yeah?
Yes. So olivine, pyroxene, plagioclase, all those, they form from crystallization of magma or lava on Mars. There's only the one that are formed through impact when they ejected, tiny. They're gonna be very high pressure minerals.
Oh, okay, yeah, thank you. And I'm from the Navajo Nation, so I thought it was really nice that they included my language in the stratigraphy as well. And I'd love to have a conversation with you afterwards if you're interested.
That's really cool. Well, thank you.
Any other questions?
And there are no questions online.
I wanted to make a quick announcement that if you're in the class, don't leave after class. After this, I need you for like 5 minutes.
All right, could we have another big round of applause for Aria? Thank you very, very much. Yeah, just put it here.
That was easy.
You're good at that.
Well, I don't.
Hello. What's up, Eric? How are you? Great to see you. Thank you. Great. Yeah, good to see you. Yeah, I was saying like I have fun. Yes. Been working late in the lab. Oh wow. Oh. 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 I don't know how to, or maybe it's wrong. That's a possibility. I mean, on this. Ah. Oh.
Kick out of that. Oh, yeah. They're out at the station. Just we were check.
Yeah. Thanks. If you're in the colloquium class, please raise your hand. $25, I count 26. I think 25 or 20, 25 plus or minus. That's fine. Thank you. You can put your hands down now. Okay, someone's in the bathroom. You're back. Okay, cool. Thank you for staying after. I don't have a lot to say that I didn't already write on Canvas. So